Now, let's talk treatment of viral infections. As I have stated before, and I'm going to state again, and you're going to listen to this and you're going to follow this. If you're going to be any type of clinician, no antibiotics for viral infections. No penicillin, no moxicillin, no cephalosporins, no tetracyclines. Those are bacterial and bacterial only. Viral antivirals are different. Now, it's not to say we don't have drugs to treat viral infections. So if you're going to be a clinician, a nurse practitioner, a PA, whatever, and somebody comes in, mom or dad brings in little Johnny, little Susie, who's got the no matter how much they beg, plead, do not prescribe penicillin, amoxicillin, tetracycline. Okay? What they have is a viral infection, a rhinovirus infection that's causing overproduction of the mucus, which is thickening, causing the snot bubbles, and it's draining down the back of the throat, which is irritating the epithelial lining of the throat. That's what's going on. Now, for a lot of the viral infections, a lot, not most, sorry, don't say most, a lot. For a lot of the viral infections, we're studying and we're trying to develop drugs that will inhibit what's going on. 3 modes of action we are targeting. Bar penetration, spike must hit receptor, remember, for viral uptake. For a virus to propagate, remember you had those steps, attachment, absorption, penetration, synthesis, assembly, release. So all those different steps, if you can find a target and develop a drug that's going to specifically inhibit that step in the process, there you go. So somehow bar, spike meeting receptor. We have some anti-flu drugs. So if you got really bad flu, it's causing issues, you take the drug, it's not going to clear up what you have, but what it's going to do is it's going to stop the flu virus that's being released from already infected cell spreading to new cells. Block synthesis. Reverse transcriptase is part of synthesis. RNA viruses like the HIV virus have to take the RNA template, make a copy that's DNA. That DNA template copy can then be recognized by host cell. Host cell reads it, makes mRNA and all that stuff. DNA then gets copied to make the viral RNA genome. That first step, RNA to DNA, we can't do that. So, perfect target. And then maturation and release. There are other anti-flu drugs on the market that will stop the release of the drug. So you already have an infected cell, synthesis and assembly has occurred, but the virus can't get out. The proteins, the machinery that are allowed to get out and develop its own envelope won't allow it to happen. That viral infected cell, given enough time, will either die its own cell, cause its own self to die, or the immune system will finally catch up and tell it to die. So you look at table 10.8 here. Table 10.8 shows some examples. Amantadine. Amantadine is the drug. It's commonly referred to as Simetrel. Inhibits fusion. Virus binds the receptor, but it can't fuse, can't get in. inhibition of nucleoside, inhibit nucleic acid synthesis. Acyclovir, great drug for treating herpes. Okay, it uses nucleotide analogs. They're going to be in the cytoplasm. Herpes can't sit there and make new genome copies because it keeps picking up these nucleoside analogs. The analogs kind of sort of look like a true nucleotide, but it's missing parts. So it can be inserted in, but nothing can be attached to it. Our cells will be only slightly affected. Our cells will recognize this as DNA damage and then replace the nucleotide analog with the correct nucleotide. During viral synthesis, the new herpes virus genome, this can't happen. This won't work. You look at Tamiflu. You've heard of Tamiflu. Tamiflu is one of them that inhibits release of the influenza virus. So again, that one cell has the virus assembling in it, but they can't get out. Give it enough time, that cell will die. It will cause itself to die, or the immune system will finally kick in, because it takes a few days for it to kick in. Once it kicks in, it tells that cell to die on its own.